Hi folks, this video is to be done in conjunction or watched in conjunction with doing the exploration here for section 9.4. Alright, so let's get started looking at sound waves. Our study of periodic functions really has a lot to do with instances where there's some kind of a wave action going on. And one good application of this would be with sound. As it says up here, we have a note, we'll call it L, that's played on a keyboard and produces this wave right here. All right, and just point out, you can see it's got an amplitude of 2, and it looks like it has a period of about 3. Okay, so now we want to graph another note. We want it to have the same pitch as L, but we want it to be louder. So what do you think would have to change about note L to make it louder? Are we talking about the period? Are we talking about the amplitude? Are we talking about the midline? Those are some of the things we're looking at here. You can pause and give that question some consideration. You may have heard the idea of measuring the volume of a note by talking about volume in terms of amplitude. And yes, if we want to make a note louder, then we need to increase its amplitude, but we're going to keep the same period, or at least try to, as we sketch a graph. Okay, something like this. Bigger amplitude, got to have an amplitude of 3, but I was trying to keep the period to still be 3. Alright, let's take a look at the next situation. This time, as you see, we want our pitch to be higher than note L, but still have the same volume. So, of course, we want to keep the amplitude the same, but what else might we change? Alright, why don't you pause the video and consider that question. Okay, well, hopefully you were thinking that we need to change the period. Okay, you may have heard, a higher frequency means that your note or your pitch is actually higher. So if we're going to go higher pitch, then we need our period to actually be smaller. That would give us a higher frequency. Frequency being like how many cycles you would have in 1 second. We need that to be more, so our period, the length of each cycle needs to be smaller. But we should try to maintain the same amplitude. Something like this. I think I had a little better luck with drawing this graph. Alright, let's take a look at the next situation. Okay, so finally here we want to keep the same pitch, but have our note decrescendo, which, as it says, gets softer. So think about what you would change to do that. Pause the video, and then you can check your answer with what I have. See if this is what you got. Yeah, something like this where we can actually see the amplitude kind of going down, right? Some way, kind of a decreasing line or a decreasing curve for the amplitude. Let's investigate these ideas a little more here by looking at their formulas. So note M was louder than note L, so if you're looking up here you can see that we have note L's formula here, so change it so that you have a note that's louder but still is the same pitch. Alright, check and see if this is what you got. Alright, so you can see I made my amplitude 3, something a little bigger than 2, but left everything the same. Let's look at the next one. Alright, now be careful with this one. It's not quite as straightforward as the last one. You want to have a higher pitch, but keep, the same volume and everything else. Why don't you pause the video and give this one a try. Alright, see if this is what you got. Now, you may not have put pi here, but you needed to put something that was bigger than 2 pi over 3. Okay, now you might have thought smaller because you need a higher pitch and you need a smaller period, but remember what the period is made up of, right? Period is going to equal 2 pi over, and at first it was 2 pi over 3. Well, we need a number that's bigger than 2 pi over 3 if we want to have a smaller period, okay, right? Because the bigger your denominator, the smaller your fraction is. So pi is a little bit bigger than 2 pi over 3, but you could have done any number larger than 2 pi over 3. You could have said 7, and that would have worked. All right, so let's look at the next situation. All right, so now with note P, we need to be, I think this is how you spell decrescendo, I'm not sure, but we need to be getting softer. So what can we change? Obviously, we need to change, this amplitude. Keep in mind that that amplitude is constant, right? Think of it as like y equal to 2 is a constant function. We need to have a function that is getting smaller, okay, or going down, right? So what might you change that to? Pause the video and give that a shot. Okay, did you write something like this? So here is an idea for getting your amplitude to decrease, right? It could be a decreasing linear function, something like that, right? Just so it's no longer constant. All right, let's look at some other ideas about this. This is kind of similar to what I had, having some kind of decreasing line. I don't think it's the same line I have, but let's just see, if we look at the next slide or the next graph, you're going to see there's a little bit of problem with having a linear situation like this. So here's the formula that we're using here, a little not quite as steep as mine, but you can see the issue is we go far enough and of course the line keeps going down, but that means our amplitude actually starts to get bigger again. So this might be a decrescendo followed by a crescendo. So how could we get it so that it would just keep, decrescendoing and not crescendo back? In other words, what formula might we use for our amplitude so that it would do something like this? Where have you seen a curve that looks like this before? Right? Pause the video and think about your answer. All right, well, if you said, this looks like it's exponential, a decreasing exponential, then you're on the right track. And we could put something like maybe 3 times, maybe 1/2 to the x right here in place of our amplitude, right? That would give us a decreasing exponential function. Okay, so we were spending some time working with the dynamic amplitude. Now why don't you try doing something that's non-constant to the midline. For instance, what do you think this graph would look like if we instead of having like cosine of x plus 3, where you would have just a horizontal constant midline and you'd be doing your cosine curve off of that. Change the midline now to x minus 1 and see what you think you get. Pause the video and make some kind of a sketch here. All right. Well, one quick way we can check your graph is by looking at the actual calculator. So see if you got what's on the next slide. Now you may not have gotten exactly what's written here, but if you got the general idea of your midline going up like this and your wave kind of going off of that midline, then you're doing pretty well. This graph does actually go through the origin if you think about it, because the cosine of 0 is 1, and so you'd have 1 plus 0 minus 1. So if you got that detail, you're really on top of things. All right, let's do some more with this dynamic stuff. Now we want to have a period that changes, all right? And so we're looking at the graph of y equals cosine of x squared, and that is a dynamic period because we could write that as x times x, which means, normally this number would be, maybe a 2. We'd have 2 times x. We're going to change that constant to some variable, and that's going to mean that our period is changing, right? Because the period, the period is 2 pi over whatever the constant is, but since we don't have a 2 there anymore, now we're just going to replace that with x, right? So you got 2 pi over x. So you want to think about what's going to happen to the period as x gets bigger. All right, so if we were to start here, what's going to happen as x gets bigger? Pause the video and see, make a sketch of what you think it's going to look like. All right, let's check and see if what you have kind of matches the graph on the next slide. This one may seem kind of wild or weird, but as x gets bigger, yes, your period is getting smaller, right? The bigger your denominator gets, the smaller your fraction gets. So this is what our graph looks like. All right. Okay. Well, let's take a look at one more thing having to do with sounds. This time we're going to compare two pitches. There is a reason that I'm using two clarinets in this one. Clarinets actually give a pretty pure tone when they play. If you were to, say, have a trumpet play a note, you wouldn't get a nice wave. There'd be a lot of little overtones in the wave, so the wave would kind of be jagging and doing things. But clarinets do produce a very nice wave. That's why I'm using them. So we're playing two notes here. And here's the equation for one of them, and here's the equation for the other. And what's going to happen if two clarinets play these notes simultaneously? In other words, let's get the equation of their sum, right? We're going to be adding these two notes together, and I want you to write the sum of that equation down here and see what you think that means is happening. Pause the video and consider that. As the paragraph would suggest, we have two pitches that are the same, right? But they do have different volumes. So when we add them, all right, we can actually combine these because since the pitches are the same, we actually have like terms, all right? Sine of x, you could treat this like 5y. Sorry, I'm having a little trouble with my pointer. We could treat this as 5y plus 3y. So hopefully you wrote down that you end up with 8 times the sine of x. All right. And so explain how we know that the pitch of sound C is the same as A and B, but that the volume is louder. Pause the video and answer these two prompts here. All right, see if this is what you wrote. As you probably had guessed, we can tell that it's because the amplitude's bigger, it's got to be louder. One thing that musicians know, especially people in band, is the more in tune that you can be, the louder your crescendos are going to be. Especially if you have a band that's playing the same note, that's about the loudest you can get. All right, because you're adding those waves and you're making the amplitude that much bigger. If you're adding the waves, you're getting a bigger amplitude. All right, let's look at what happens now when the clarinets play a different note. So if the instruments play two different pitches, then we are going to have different periods, right? So let's go ahead and figure out what the periods for notes D and E are. Pause the video. Okay, see if this is what you got. All right, so we should have a period of 6 for note D, as you can see, dividing 2 pi by pi over 3. So actually your pi's will cancel and leave you with 6. And then we'll have a period of 4 with note E. All right. So which pitch is higher? If you said note E was higher, that would be correct, right? It has the smaller period, so its frequency would be higher in the sense that you'd have more cycles in a certain time limit. All right, let's continue with this. So if we play these two notes at the same time, it's like we're adding their equations together, all right? And this would be the curve that we're going to get. So it might be a little hard to see, but this is actually periodic. It does start to repeat. So from this graph, see if you can figure out what the period is. All right, pause the video and give that a shot. So if you look closely at it, so you might see it comes across the x-axis, goes back down kind of narrowly, and then goes back up and then down a lot. And you can see like over here it kind of does the same thing, up a little bit, down a little bit, and then up a bit more. So the repetition is happening right in here. So if I look at this point right here, that would be what, 1, 2, 3, 4, 5. We're at -6 there. Let's write that. So that's -6. And if we go and find that same point over here, I believe that will be +6. 1, 2, 3, 4, 5, 6. Yeah, this is +6. All right, so I believe from the graph we can see that the period is 12. You know, if it's not real evident here, you could certainly on your calculator get a bigger window. I'm going from -10 to +10, but if you get a bigger window, I think you'll see it does take 12 units to start repeating again. All right, so let's see what the relationship is now between all of these periods that we have. So we have the graphs of our two notes that we were playing. One of them, as you remember, has a period of 4 and the other one has a period of 6. And we've opened this window up, as it says, to go from 0 to 12. So you can kind of see what these two graphs are doing between 0 and 12. All right, and we're trying to find that relationship between these two periods and the period of the sum. Here you can see all three graphs going from between 0 and 12. I'm not sure if that clarifies things, but it's your turn now to make a conjecture about the relationship between the three periods and then to try to explain why they have that relationship. Okay, so we want to state the relationship. We've got the period of sound F, which is D plus E, is the blank of period D and period E. So 12 is the blank of 6 and 4. All right, I'll give you a hint on these. There are three, it's like a three-word term here. Starts with an L. That's the initial of the first term, L. And then the second word is C. And the third word is M. Okay, so hopefully you can figure out what that is with that clue. And then the big part is, you know, when you go back and look at the graphs, can you see why the period of the sum of the two sounds is the LCM of the other two periods? Look at the graph carefully and see if you can explain why this happens. All right, I will leave that for you to do, and be ready to perhaps hand your sheets in to verify that you've done the work. Okay, we will see you in class.